My name is Nick Zernecki. I'm the Global Marketing Manager from Melexis, joining you from my wonderful basement here. I tend to talk a little bit fast. I'll try and make sure to slow down here. If you have any problems understanding me, just feel free to flag it in the chat, and you can pop in and tell me to slow down. Otherwise, we can go ahead and get started. As you see on the screen here, this is the MLX 90395 product launch webinar, which we officially launch tomorrow, or today, technically. And this is sorry, my screen's not advancing. There we go. So in terms of what the webinar will cover, we'll cover what the MLX 90395 is, what the differences are to the previously launched MLX 90393 device, which was released about 3 years ago, what the similarities are to the MLX 90393, some example magnetic setups for different types of motions, rotary linear joystick, including multi-DOF types, and then example applications the MLX 90395 is either used in or being designed in today, or could be used in future applications. So in terms of what the MLX 90395 is, this IC is a 3D magnetic field sensor designed to sense X, Y, and Z magnetic fields. It's basically a magnetometer. Unlike other magnetometers though, the 90395 senses magnetic fields produced by permanent magnets. Earth's magnetic field is around 25 to 65 microtuscles in strength. The 90395 senses in the range of 5 to 50 or 5 to 120 millituscles. So it's quite a few orders of magnitude in difference. And therefore it really is designed to be acting as a position sensor for permanent magnets. Unlike many other devices in our portfolio, the 90395 is also designed to be a companion chip. So it's a embedded device, intended to be paired with a host microcontroller, not a standalone device like our previously launched 90371, 90372 devices. It's not designed to be operated on a very long harness where we have a lot of EMC events or ESD events. It's really designed to be paired with a microcontroller with a regulator next to it, maybe a transceiver that does all the protection for the 90395. And the SPI and I2C interfaces really help to enforce that. In terms of where it slots in the portfolio, so in terms of full 3D, so devices capable of measuring X, Y, and Z, we had the former 90333 and 90363 devices, still in mass production, still available, and we simply expand the portfolio with the 90395. And you can see a kind of progression there in terms of content inside of the ICs. The 90333 was the first joystick device, offered analog, PWM, and SPI output, had a microcontroller inside to do the processing of the fields and the angle, to compute the forward, backward, and then left and right motion of the magnets for joystick applications. And because of that, because it had a DSP inside, it was really drawing about milliamps of current, typically greater than 10 milliamps per die, and on a 5-volt supply. The 90363 shrunk it a bit, only SPI now, still had a DSP inside of it, computing the magnetic angle, but also offered XYZ output. And then was still milliamp power, a little bit less than the 90333, but still, 5 volt or 3.3 volt supply, but in the range of 10 milliamps. And the 90395 now really shrinks things down, changes from a DSP inside to a finite state machine, which allows us to really optimize the power draw and have a kind of duty cycle measurement that we'll talk about more in a few minutes. We also expand things like the package options for the 90395 from the 90393 to also offer a dual die version, which again we'll mention in a few minutes. In terms of the differences between the 395 and 393, I know many of you have probably been using the 90393 for some development work, or maybe for some non-automotive or consumer applications. The biggest difference between the 90395 and 90393 is that this IC is automotive qualified to AEC Q100 and also offers a wider temperature range of -40 to 125 degrees Celsius. And that's ambient temperature range. The previous 90393 only went up to about 85 degrees Celsius. This makes the 90395 more suitable for on-chassis or in-cabin applications, like body sensors, door handle sensors, perhaps some other devices like powertrain, like pumps or valves, as well as some industrial purposes like joysticks or material handling equipment like pushers or pneumatic cylinders. The speed is also doubled. So the 90395 goes up to 2 kilohertz, and that's 3 axes being converted. So X, Y, and Z. Formerly, it was only up to 1 kilohertz. This is actually for 3 measurements, kind of in general. So if you only need to measure X and Y, for example, for rotary motion applications, you can also convert X, Y, and T while still maintaining the 2 kilohertz sample rate. This is quite useful for applications that require a bit faster closed-loop response time, perhaps like a pump or valve, where you have a motor inside of it. You need to be able to control the actuation speed and the method. The Nano 395 also offers the ability to measure its own supply voltage. So this feature is included to allow a detection and a diagnostic of the analog signal chain. So the Nano 395 can read its own ADC or its own supply voltage through its ADC and output that value to the host market controller. The host market controller can also measure its own supply voltage, and assuming that they are both operating at the same voltage, if there is a match, then things are generally going okay, no failures. If, however, there's a mismatch between the supply voltage measured by the 90395 and the supply voltage measured by the market controller, that can indicate a failure somewhere in the system, either with the 90395 signal chain or with the market controller's ADC. And in that case, a diagnostic can be set and a safe state entered. The supply voltage can also be used to measure battery discharge for battery-powered applications. The 90395 also offers a new magnetic field range. So the 90393 previously only ran from 5 to 50 milliteslas on the X and Y axis. We offer that same field range for the MLX 90395, but we also expand it to a new range of 5 to 120 milliteslas. Why we did this is for 2 reasons. One is because a higher magnetic field allows for closer air gap. So for things like very small joystick applications, the magnet can approach very close to the sensor and therefore apply a very high magnetic field. As the joystick moves the magnet away, in the case of a ball and socket design, that magnetic field strength can weaken quite a bit. And therefore, when you let it spring back, you have a high magnetic field, and therefore you do not want to saturate. The higher magnetic field also reduces the impact, but does not nullify the impact of stray magnetic fields. And there's a rough rule of thumb for this, where 1% of the good field applied as a bias field or a stray field will equate to about 0.6 degrees of nonlinearity or error. So for a rotary application, if you apply 50 milliteslas of good field from the permanent magnet, and you apply 0.5 milliteslas of bad field from another permanent magnet or from a current carrying conductor, like you might find in electrified vehicles, you get 0.6 degrees of nonlinearity present. If you, on the other hand, have a 120 millitesla good field, the error is correspondingly reduced linearly. So it'll be reduced by about half. The Z field on both versions remains the same, so it's also 130 milliteslas peak, and that applies for both the XY 50 millitesla variant and the XY 120 millitesla variant. So the Z-axis peak field is the same in both cases. These 2 field ranges are differentiated by an order code. So inside the product name, there's a 3 number at the end. The 3 numbers indicate whether or not the medium field version or the high field version is being used. The protocol was also enhanced on the 90395 versus the 90393 in that a CRC was added to ensure the data integrity of the measurement is ensured during transmission. So the CRC will cover the magnetic field transmissions along with the supply voltage and the temperature to ensure that the data going from the 90395 to the host market controller is not corrupted. The total number of values being transmitted is also selectable, depending upon the axes desired to be converted and on the particular command used to trigger the IC. In terms of packages, the 90395 comes in the same 3x3mm QFN16 package that the 90393 comes in, but we also expand the option to include an SOIC8 package and a TSSP16 package for customers that don't want a leadless package. There's no difference between them. The only difference is that the pinout of the SOC8 and the TSSP16 packages are a bit reduced in content simply because there's less pins available. You see that's highlighted here. The A1 pin on the SOC8 and the TSOP16 package is missing, and the interrupt and trigger pins are combined into one. The TSOP16 package is also fully redundant and contains 2 individual dies. So there are no shared wires, power, ground, or output between the dies. And I like to joke that if you took a very thin saw or laser and you cut the package down the middle, you'd wind up with 2 TSOP8 packages. Of course, I don't recommend that, but theoretically it's possible. The benefit here is that if one die experiences a malfunction or a short circuit on one of the I/O pins or on the supply and the ground pins, the other die remains unaffected. And you can use that secondary die to either continue normal operation, flag a diagnostic to the operator, or go to a limp home safe state mode. In terms of similarities between 395 and 393, they're both a very small size solution. You see a 2-scale image on the left with a eurocent. Apologies to my US colleagues. I don't have a good rendering for a US penny. If any of you know that, feel free to send it to me. But again, quite small. In terms of the packaging envelope or the total volume that takes up, I say that the TSOP16 package or SRC8 package takes up generally less than 1 cubic centimeter of space, and that's including a 6mm by 3mm diameter magnet. The total space in terms of area will of course depend on the amount of external components used, which are represented as these little capacitors there. Of course, for I2C lines, you have to have the pull-up resistors, and generally we have some additional EMC filtering capacitors on the data lines. But overall, it's a very small, very compact package. The 9395 also operates off a 3.3 volt supply and operates in a kind of duty cycled way. And what I mean by that is that the current draw is variable over time and has a high peak measurement current when it's doing a magnetic conversion. So when it's actually doing a data acquisition, the chip is awake, the Hall plates are active, and it draws about 4 milliamps of current maximum, worst case in all conditions. And when it's not doing the acquisition, it goes back to an idle or standby mode where it draws a maximum of 20 microamps, again, over all conditions. That's temperature and supply voltage. Therefore, the total current draw really depends on how fast you're acquiring the data, your duty cycle, and how long you're in that measurement state. And we'll talk about that more in a minute, but there's some trade-offs you can do to optimize both power, speed, and noise. The longer you take to convert, so that width here where it says measuring, the width of that high current area will affect the noise and the speed. The longer you take to convert, the less noise you have because you're basically filtering and oversampling the data. However, the longer you take, the more power you draw because you're in that 4 milliamp state longer. And of course, your speed will slow down because you take longer to convert, which means you can't sample as fast. You can also do the opposite trade-off. If you want to go very, very fast, 2 kilohertz rate, for example, you can crank down the filtering and you can sample very, very fast with a fast duty cycle. Therefore, your speed is fast, your power is reduced, but you pay a penalty and some noise. So really this triangle is fully selectable. There's some registers we'll talk about more in a minute. And you can basically place your dot, your operating condition, wherever you want along the triangle. And as I was saying, many of those parameters are programmable. So gain along with sensitivity and resolution to tune the ADC range to the magnetic field. So for example, my rough rule of thumb is that you want to have about 80% of the ADC span utilized in the MLX 90395. And you can tune that with the gain and then the sensitivity and resolution. The measurement axes are also selectable. So any combination is possible. If you want to measure only X, you can measure only X, only Y, only Z. Combinations of 2, XY, XZ, YZ, or all 3, X, Y, and Z. The temperature and the voltage is similarly selectable. So if you want it or not, that's also choosable. And that's programmable through either a command being sent on the fly, or you can set it inside the registers of the non-volatile memory. The oversampling of the filtering rate is also programmable. That's what we talked about more in the previous slide, where you can tune the speed and the power consumption and the noise to the desires of the application. And then the conversion rate or the duty cycle is also programmable. And what I mean by that is there's 3 modes of operating for the MLX 90395. You can have it as a single measurement where the device gets triggered either via a trigger pin or a message. It acquires the data and then flags that's ready. That's fully controlled by the microcontroller. Then we also have a burst mode or a free running mode where you can simply tell the IC to start running. It'll start converting the axes that you select on a programmable time interval and a programmable duty cycle. So the chip will wake up, convert, fall back asleep. Wake up, convert, fall back asleep. And that time between them is again programmable. Then we also have wake on change mode, which is the same as burst mode, where the chip wakes up, measures, and falls asleep. However, now it'll do a conversion and it'll do a comparison. So it'll acquire the data and check if it's greater than the threshold that's programmed, again, by the user. If it exceeds that threshold, the interrupt pin will be set and it can be used as a flag for other devices in the system. The temperature parameters are also readable. So things like offset drift and sensitivity drift can be used to compensate for thermal variation in the system. And then we have some free space for things like traceability information, lot code, date code, serial number. That's all programmable into the IC. One thing to note is that it's not like a flash memory. This is designed to be written a few times, not many, many, many times. The protocol is also the same, so SPI and I2C, where SPI can operate up to 10 megahertz clock frequency. I show here a 4-wire SPI, so a full duplex. Half duplex is also possible, and therefore only takes up 3 wires. There's an example application in the data sheet near the end that shows how to configure that. For I2C mode, it operates up to 1 kilohertz in the standard mode, or up to 1 megahertz in the fast mode. The I2C address also has 1 or 2 hardware selection bits, as mentioned earlier, A0 and A1. In the SRC8 and T-sub16, though, remember that there's only 1 address pin available, meaning that you can pick between 2 different addresses, versus the QFN where we can select between 4 different addresses. And the motion types are all the same as well. So rotary on-axis, off-axis, linear joystick, including push, which we'll talk about more in a minute, for both rotary on-axis and joystick. In terms of magnet configurations, the first one we'll mention is the rotary on-axis motion. This is by far the most common. And on-axis simply means that the shaft, the magnet, and the sensor lie on the same common axis. So here's the shaft in black, the magnet in yellow and blue, and then the sensing spot is basically in the middle. And all of these pieces line up on the same axis. It's 360 degrees of rotation. Going above that is not a problem. The waveform simply repeats. So it goes and then resets, increments, and then resets. It's both clockwise and counterclockwise. So doing it the other direction simply means that moves right to left instead of left to right. It's also an absolute position sensor, meaning that you could take the magnet away and put it back in the same orientation, and the position computed will remain the same. It also means that you can power off the sensor and power it back on, and the, again, angle position remains the same. Since it's magnetic based, it's non-contacting, which means it's immune to dirt, dust, or liquids, like all of the other Traxxas devices. And the 90395 is also capable of detecting push and pull. So you can do a kind of selection with the Z-axis motion. And what's important to note is even if you're doing the Z-axis motion, push and pull, you only need to measure the X and Y axes. And that's because, as you'll see in a minute, the magnetic fields applied are acting as a sine cosine. And that tells you the angle, and the magnitude will tell you the push or the pull. It's also insensitive to air gap or thermal variation. So in terms of the air gap between the sensor and the magnet, As long as the magnetic field is within the operating field range, 5 to 50 milliteslas or 5 to 120 milliteslas, depending on which version you're using, the sensor will operate correctly, and there will be very little to no deviation due to an air gap variation. The same thing applies for thermal variation, and that's because the fields for X and Y will weaken or strengthen proportionally. And as we do an arctangent computation on the two different vectors, it means that as this field weakens, let's say the green field, the blue field will weaken the same amount, and the ratio here for the arctangent will remain the same. So this is a very nice result of that. If you have an on-axis rotary motion, even if your air gap varies a bit, or if you have a ferrite magnet that can vary a lot in field strength because it has a negative 2000 ppm per degree C thermal coefficient, the angle remains the same. You don't have to worry about compensating the position over thermal variation or air gap. And that's all because we use more than one magnetic field to do the computation. One thing to note as well, this computation is done in the host microcontroller. This is not done in the MLX 90395. So this is software that would typically be done by our customers, and we can assist with that inside of the host microcontroller. So to compute the angle, that tells you how much you're rotating the magnet. To detect the push or the pull threshold, you see in the red dotted lines here, the norm simply needs to be computed. And this is basically like you're translating the system into polar coordinates. We have an angle that tells you the rotation and the magnitude that tells you the radius. When you push the magnet closer together, the norm will get bigger. It's a higher field strength. Likewise, when you pull it away, the norm will get smaller because it's a lower field strength. And thresholds can be set up inside of the host microcontroller to detect that push and the pull threshold. So as the magnet is simply rotating, it normally follows the same radius or the same norm because there's not a whole lot of variation during rotation, and there's probably not a whole lot of thermal variation going on all at once. It's probably operating in a relatively static temperature range. However, when you push it and the magnet suddenly moves closer, the norm will jump and it can exceed that push threshold, and the microcontroller can detect that a push has been detected. And the same story, but vice versa when you pull the magnet away. In terms of linear or slide motion, this is probably the second most common. And this is where the sensor lies above or to the side of the magnet. So in these images, they're all above, but the magnet can also be placed off to the side of the sensor. Important to note is that this system still computes magnetic angle. So still use an arctangent, which we'll see in a minute, and mapping to millimeters is typically done via calibration or learning step. This is also important because linear motion applications typically have worse nonlinearity than a rotary on-axis motion, especially near the ends, and also depends on the size of the magnet you're using. If you use a small magnet but a long stroke range, your nonlinearity near the ends will typically be worse, and therefore some calibration points are generally recommended to be done inside of the host microcontroller. It's still an absolute position sensor, non-contacting again. And again, like the X, Y axis for the rotary on axis, only X and Z or Y and Z axes need to be measured. Again, it's insensitive to thermal variation, but one thing to note is that it's more sensitive than rotary on axis motion for air gap variation. When the magnet is directly above the sensor, you can imagine that the magnetic field is entirely concentrated in the Z-axis, going into the IC package. In that position, it's quite immune to air gap variation. However, as the magnet moves further away, the magnetic field lines do vary and the angle will vary as the magnet moves up and down. There can be some tricks to help mitigate that via processing that can be done in the host microcontroller, and we are more than happy to help you with that effort. You see an example X and Z field plot for a relatively long 40 millimeter stroke range, plus or minus 20. The computation to detect the position is still the same. So the difference here is that it's X over Z or Y over Z, but the norm stays the same. So you can still compute the norm, which allows you to optimize the magnetic field and the gain. And then what also happens is that the magnetic angle is typically converted to millimeters or to some mapping to map the magnetic angle to a given position. For example, you could put a calibration point all the way to the right, one in the middle, and one to the left, and that will help you compensate for some mechanical nonlinearities in the system. And in terms of 3D and joystick motion, here's the magnet typically placed above sensor. We'll see a picture in a minute. And it can sense up to 180 degrees or more, depending on the mechanical setup. So most of the joysticks, of course, will sense less because most of them aren't moving all the way down to being completely flat on one side or the other. It's again, absolute position sensing, non-contacting, and like the rotary motion, is also capable of detecting push and pull. So it's really a 3DUF sensor then. All 3 axes need to be measured, unlike the previous 2, which only had 2 axes that need to be measured. And again, since it's a relative measurement using more than one field axis, it's again insensitive to thermal variation for the magnet. One thing to note is that there's really 2 different types of joystick motion. There's the gimbal design and then the ball and socket design. The gimbal design is distinct from the ball and socket in that the pivot points are in line with the sensor. So if I draw those here, it's not the greatest color, I apologize for that. And if we draw one going this way, you can see that the pivot points, these little black stubs, really intersect the center of the IC, or the sensing point. That means that the air gap remains constant over the entire pivot range, from 0 degrees to 180, if that's desired, in both forward, backward, and left and right motion. The ball and socket configuration, on the other hand, has this pivot point above the sensor. The magnet has a pivot arm or pivot length, and therefore the air gap varies. So you can imagine it travels in a kind of arc, and as it moves in the arc, the magnet moves away from the sensor. This means that there's no longer a one-to-one correlation between the amount of pivot on a joystick and the amount of magnetic angle calculated for the ball and socket configuration. On the gimbal design, on the other hand, there is a one-to-one correlation. If you have the joystick centered above the IC and you move it 45 degrees, generally the angle calculated will descend to 45 degrees. For the ball and socket configuration, that's not necessarily the case. That means that there's generally worse nonlinearity for the ball and socket configuration, but this can be compensated for again with multi-point calibration, with good magnetic design, and with some slightly more complicated formulas to calculate the position of the ball and socket joystick. In terms of the angle, how it gets calculated, so the angle is computed from the X, Y, and Z fields. You see a Y and Z plots in the bottom left. Unfortunately, I could not figure out how to plot a 3D field in Excel. So I hope that you can imagine that the BX is into the paper, but it's really the same as the BY because this is a symmetric application, and forward backward is basically the same as left and right, just with different axes being used. And since we use all 3 magnetic field axes, we compute 2 angles now, forward, backward, left and right. And that means that the previous example where we had a polar coordinate system turns into a spherical coordinate system, where we have 2 angles and again, a field norm. Not shown here is a pull threshold for clarity. However, a pull threshold can also be used. In this case, you can imagine that you have a sphere. The magnet is riding on the surface of the sphere, and as you push and pull, the radius or the diameter of the sphere increases or decreases. For the gimbal design, because it has a constant air gap, the magnet is effectively acting like a rotary motion, but in the X and the Z axes, or the Y and the Z axis. Therefore, the magnetic angles, the calculation for those, is much simpler than with the ball and socket design. The field norm remains the same between both, so simply the square root of the sum of the squares. And then for ball and socket, it's a little bit more complicated, and that takes into account the fact that there's usually some additional field variance in there. When you have the ball and socket, it's not a perfect symmetric field anymore. And you also have a variable air gap. In terms of application examples, so the first one that we'll talk about is the selection or the headlamp switch. So you see that on the screen. That's purely to turn on or off the park lights or the headlights for the car. The push and pull functionality is used in this case to turn on or turn off the front or the rear fog lamps. So the rotary motion turns on the headlights, and then you can pull the switch to turn on the front fog lamps and push to turn on the rear fog lamps. Doing that motion again will simply turn off the respective fog lamps. This is a nice solution because it enables a non-contacting solution, particularly useful for things like heavy vehicles where you may want to wash out the inside of the cabin. You don't want to have to worry about liquid intrusion. It also helps reduce part count and simplify the design because there's no need to use things like a tactile switch anymore to detect that push and pull functionality. In terms of using the device, the items to set and configure is actually quite straightforward. The gain needs to be set to maximize the use of the ADC span. Defined gain can be tuned by the resolution or the sensitivity parameters. And then the digital filter and oversampling register can be set to optimize the power, the speed, and the noise. Measurements simply need to be started then. You can either use a single measurement, the burst mode, or the way can change. And all that needs to be converted are the X and Y axes. If it's desired to measure temperature, the die temperature can also be measured, which can give an indication of the ambient temperature. And the supply voltage can also be measured. Then all that needs to happen is that the angle needs to be processed inside the microcontroller, which will help determine the position of the magnet and therefore the position of the switch. We also have some additional devices that can be used for this application. So we have Melexis LIN switches that can be interfaced to the MX90395. And this allows a two-chip solution to be connected to the host ECU via LIN. The MX LIN switches include things like the integrated I/O, the voltage regulator, the LIN transceiver, meaning that this is really, again, a small, compact two-chip device. It also offers some LED lighting capability to illuminate the various lights like you see on there for the front, rear, and the headlamp indicators. Since it's LIN-based, it's also a 3-wire solution, which is very compact in terms of wire harness count and therefore cost. Next application is the turn signal stalk or multifunction switch. This is a simplified mechanical design, of course. In actual application, this can be much more complicated to ensure that the return to zero is done, as well as additional mechanical features to tune the feel, like with the springs, for example. The benefit to the 9395 here is that it enables non-contacting sensing. So again, immune to liquid, dirt, and dust. It enables joystick motion for up, down, in, out for the turn signals, as well as the headlamps. So the high beam toggle or the high beam latching. The 120 millitesla version is quite suitable here because there's usually close air gap required because packaging is quite small. And the digital protocol also enables easy integration to microcontrollers and allows for diagnostics. That's one thing that's a benefit over the sliding contact approach. With sliding contacts, it's difficult in some cases to diagnose if there's a fault in the system. But with digital protocol, you can really detect if something is going wrong. And since it's a small application, the 3x3 by 1 millimeter QFN16 package fits quite well into these applications. In terms of setting and configuring it, it's again very similar to the Rotary applications, setting the gain, the digital filters. Difference here, of course, is you need to select all 3 axes to do the computation. And then it's basically the same as we discussed earlier. The microcontroller tells the MX90395 to start, reads back the data, and then processes it. Interesting thing, but not implemented yet, is that the twist functionality to detect things like windshield washer speed can also be done, but would require additional sensor and magnets down here at the end of the stalk. And then the wires could run down here, and then the I2C or SPI protocol can then be connected to the host microcontroller. The 90395 can also be used for valve position detection, where the flexible nature in terms of axes being converted can be an asset. Many of these sorts of small coolant valves do not have access to the end of the shaft to place a magnet to sense the rotation of the valve. However, they do have access to be off axis. It's a bit of a tongue twister. So for example, here you see that the sensor is placed off to the side. PCB could be underneath this, for example, and the shaft could run down to connect to the valve, to the motor, or to some gear train to control the valve position. Again, we have a two-chip solution. We have Melexis drivers that can be operated over LIN or PWM, interfaces to the 90395 IC, and this really acts as a closed-loop system. So the driver IC controls the motor, which then is read back through the 90395, and so on and so forth. And the data is simply transmitted over SPI I2C. This enables the driver to control exactly where the valve position is. Again, same items to set to configure, same basic configuration, gain, fine gain, digital filter. The difference here, of course, is that the axes depend on the magnetic setup. So XZ, YZ, or X and Y. And again, all the data is processed in the host microcontroller. However, every application is different. We've only covered 3 today, the headlamp switch, the multifunction switch, and a valve. We have some getting started material available. So a getting started guide, which you see on the right, which is designed to be used with an embed tool. An example is down at the bottom right, where you see an embed based on the LPC 1768. We also work on some evaluation boards. Unfortunately, they're not quite ready yet, but they will be coming in the next couple of weeks. And then we will have a video demo for eNob. You can find that online at the link. That's not for sale, but it's a really cool application with rotary motion with push detection that illuminates a variety of LEDs, and it changes colors based on if you push the knob. Very useful for showing things like HMI applications, especially for things like white goods. We may have a big knob for like washing machines to detect different cycles and then push to select, for example. We have some code samples available. We can distribute those to you as well. And if you have any questions or need more information, you can feel free to contact us at the link below through our distributors or through our local sales contacts or our local sales representatives. That was it from my side. Took about 14 minutes, so I hope it was interesting and informative. If you have any questions, I'll be happy to answer them now.
Thank you very much, Nick. That was very comprehensive. We actually have quite a lot of questions for you already, so we'll probably start with these, but please submit your questions to the Q&A or chat and we'll get back to you. So the first one is on functionality. So the functionality of the sensor is defined through the system processor instead of hardwired into the device itself. So what are the benefits of this approach?
Yeah, the benefits of offering basically the Traxxas core as opposed to on-chip processing is that the flexibility is therefore offered. So by offering a XYZ output sensor, the host microcontroller can process that data however sees fit. So right now we talked about 4 different types of motion: rotary, on-axis, off-axis, linear, and joystick. Those are just the 4 primitive types. They can actually be combined in other ways. So you can use a joystick type sensor, but also in a kind of translation as well. And by allowing that flexibility and that freedom in the host microcontroller, it means that our customers can then integrate the 90395 into a wide variety of different applications, requiring a wide variety of different motion types.
Perfect, thank you, Nick. There's so many questions going through. Right, the next one is in supply voltage. So what benefit does the supply voltage measurement feature deliver in practice for industrial applications in particular?
Yeah, I would say it doesn't necessarily deliver a benefit for a specific application, but what we see, and I have a little poll for this, which could be interesting. is that 3.3 volt is more forward-looking or more future-looking for the variety of microcontrollers that are coming on the market today. So I'm going to launch a little poll here to get your feedback as well, to see how you as engineers and designers and our customers really see the translation or the need for 5 volt versus 3.3 volts. The previous webinar was pretty interesting for this in terms of what is needed in terms of supply voltages, 5 volts or 3.3. And as I can already see that the variety is a little bit different than earlier this morning, which is interesting. But for embedded devices, going to 3.3 volts allows for lower power consumption and therefore better battery operation, as well as some interfaces to the host microcontrollers. I'll leave the poll up. Feel free to answer in your time. We can then move on to the next questions.
Great, thank you so much, Nick. So next question was on power consumption. So how did you achieve such low power consumption?
Yeah, again, it's based on the duty cycle concept and removing the DSP inside of the IC. So by really offering just the Trax core, which is the Trax technology up front, the gain stage, and then the ADC, all controlled by a finite state machine, we're really able to reduce the amount of power required in the IC. So by offering the selection or the option to convert at desired times and how long to convert, that really allows our customers to tune the power consumption and therefore allowed us to offer a lower power consumption device. And it basically comes down to the architecture of the IC.
Okay, thank you. And how to determine minimum and maximum working air gap between sensor and magnet?
Yeah, the best way to do that is usually via a quick simulation. So the IC has two different field ranges available, distinguished by the option code or the order code, 5 to 50 milliteslas or 5 to 120 milliteslas. And the air gap will determine which option code you need to use based on the desired magnet. So if you're using a ferrite magnet, let's say a small ferrite magnet, that's a relatively weak device, probably need a closer air gap, and therefore that will then achieve the target magnetic field range. If you're using a rare earth magnet, of course, you'll need a bit bigger air gap, but it really comes down to calculating what the magnetic field output from the magnet is at a given air gap. So for the majority of applications, like Rotary on axis, there are a lot of tools out there because you don't need a 3D tool for that. You really only need a 2D magnetic field simulation tool. And there's a lot of online web calculators. I use one from Magnet Fabric, for example, that is a magnet supplier. You can also find field plots from magnet vendors like K&J Magnetics. They have PDFs that show the field range in a nice color-coded manner. And we can also help you generally with some quick simulations as well. So as long as you select the right magnet, you can then pick which air gap or detect which air gap you're going to need to operate in. On the other hand, if you know the air gap that you want, you can size the magnet chemistry, the magnet shape, for example, to the application and to the air gap requirements.
Great, thank you. Next one is, what is the typical time to go from the idle state to the measuring state?
Ooh, that one I don't know offhand, but we can get back to you. That will be in the data sheet, but I don't know the number off the top of my head.
No problem, we can follow up with that later. These are getting tricky. What if I want to measure several joints side by side? How close can they be without interference?
Again, the best case for that is to do a magnetic simulation to see what, let's say, stray fields are going to come from adjacent magnets. We have some applications where they are operating pretty close to one another, but we have other applications where they're also operating close to each other with some interference. One possibility there is to use the 9395 paired with one of our other devices that has a stray field operating mode. And then you would use 9395 plus analog output part or PWM output part and therefore the other device that has a stray field immune mode would therefore be less sensitive. The other option is to use some shielding, which is of course not too desirable, but it can be done. You can put a little magnetic ring around the IC to prevent magnetic field from leaking, basically, or from being detected by the other sensors and the other magnets.
Great,
So,
thank you. Is there any difference in power for the strong versus weak magnetic field sensor?
there's not. So the power consumption remains the same. The only difference is that the front end is tweaked a bit, so different magnetic field range, but the average power consumption remains basically determined by the duty cycle and the acquisition time you have, not by the maximum magnetic field range.
Okay, great. This is more like an open question, but would you be able to discuss application as a distance and angle sensor, like holding a magnet between 1 and 10 centimeters from the chip and detecting that distance and perhaps the XY position related to the chip?
Can you repeat the question?
Yes, sorry. I speak very fast sometimes. So this question is asking if you could discuss in a more open way application as a distance and angle sensor, like holding a magnet between 1 and 10 centimeters from the chip and detecting that distance and perhaps the XY position related to the chip.
Yeah, so that sounds more like a 2D translation motion with z-axis motion.
Sorry, Nick. I got another question relating this. It was relating to sensing 1 to 10 centimeter distance. I might have got this wrong earlier. Does that clarify it all?
Okay. So generally the distance that we say the IC can measure with a linear motion, so like you see on the screen, a back and forth, is, let's say, 30 millimeters, and that's a symmetric distance, so it's plus or minus 15. You can make it longer. Generally, you can use more than one magnet in a specific configuration, or more than one sensor, which of course is not always desirable. But depending on how you set up, you can detect, let's say, translation motion that way and that way on the same plane, so it kind of moves in a sliding motion. And then you could also detect the z-axis motion as well. How that can be done probably needs to be investigated a little bit more in detail to see what the magnetic field looks like as the magnet moves around. 10 centimeters is probably quite a bit. It depends, of course, on the magnetic field strength that's being applied, especially if the 10 centimeters is far away in terms of the z-axis. If it's 10 centimeters in the x and y axis, that could be done, I expect, but would probably need more than one magnet.
Thanks, Nick. I hope that answered your question. If it didn't, please come back to us and we'll get back to you in case I got it wrong. Now on to noise immunity. So what noise immunity does the 395 have?
In terms of immunity to straight magnetic fields, the immunity that it has is based on the strength of the good magnetic field applied. So it does not operate as a differential sensor. It's not a stray field immune sensor. It really detects all magnetic fields. So if you have a very weak good magnetic field and you apply a very strong bad magnetic field or bad magnetic noise, the sensor will be disturbed by that. Therefore, it's important to apply a strong, good magnetic field from the permanent magnet that you want to sense to make it immune, or not immune, but insensitive to stray magnetic fields or stray magnetic noise.
Okay, great. Next question is on commercial availability. So when will the 395 will be commercially available?
It's available today. You can find it on a variety of our distributors. Not every package is available. The TSSP16 package, for example, will come more towards the end of June or early July. But you should be able to find the QFN and the TSSP16, or the QFN and the SOC8 packages available today.
Thank you. I hope I got this question right. Does the 393 Was that air gap insensitive, or is it only the 395 that has that feature?
They both are. So the air gap insensitivity comes from the fact that the processing of the magnetic angle is done in a ratiometric manner. So by using X and Y field axes, regardless if it's the 90393 or the 9395, or even our other Traxxas devices like the 90316, the air gap insensitivity is assured via the processing of the angle. So the fact that we measure here the arctangent of X or Y, or even we can generalize it to arctangent of B1 over B2, where B1 and B2 can be X and Y, XZ, YZ. By doing that, that is what gives us the air gap insensitivity for the rotary motion applications. That's partially true for the linear motion. Again, it's insensitive when the magnet is above the sensor, more sensitive when it's away from the sensor. And the same thing applies for the joystick. So as you push the joystick or pull the joystick, it's relatively immune to air gap variation when it's perfectly above it, a little bit more sensitive when it's off to the side. But again, processing of the sensor or these signals can help improve that insensitivity to air gap variation and to temperature.
Okay, great. Does it have on-chip angle computation feature for both on-axis and off-axis configuration?
No, it does not. So the 90395 is only the front end of the Traxxas devices. So if we look here to the block diagram, there's the Traxxas front end, mux to select the different measurements, the gain stage and ADC. And the finite state machine here simply controls the various blocks. It does not do any on-chip processing beyond some temperature compensations. Therefore, all of the angle calculation or the position calculation needs to be done in the host microcontroller. There's no angle processing calculated in the 90393 or the 9395 itself. So that's all done here on the MCU.
Perfect. Next question is the ASIL rating. Is the 395 ASIL rated?
It is not. So the 90395 was designed outside of the ISO 26262 norm. However, we do have a safety manual available to allow for integration into ASIL rated applications or items. And we are more than happy to help support you with that integration activities.
Great, thank you. I got a couple of questions on pricing. Would you be able to elaborate at all on the pricing against the 393?
Again, that's difficult to answer because it depends on the commercial situation behind the business, of course, total volume, SOP, those sorts of things. But roughly speaking, they're quite comparable in that regard.
Okay, that's understandable. This one is also a very interesting question. So would you be able to give any examples of situations where you should not deploy this device?
I would say in applications where there's a very strong straight magnetic field. An example I used earlier was for aluminum smelters, where apparently fields of 100 milliteslas, 120 milliteslas, 150 milliteslas can sometimes be present. In that case, the 90395 will definitely be disturbed by those straight magnetic fields, regardless if you have a very strong permanent magnet being sensed. The other areas where it cannot be used are standalone applications or where you have a very long wire harness because it only supports SPI or I2C operation. And those protocols are not designed to allow for a very long wire harness in that case.
Great, thank you. A couple more questions come through already. This one is about magnet shapes. So can you use any other magnet shapes than the ones you described earlier?
Yeah, the ones I showed were all round, either axially magnetized rod magnets or they're diametric magnetized disc magnets. There are also a couple of ring magnets. Really, any shaped magnet can be used. We have some customers using square magnets, hexagon magnets, ring magnets again. Really, any type or shape of magnet can be used, from ferrite, rare earth, alnico, for example, to square, round, disc, puck, hexagon, those sorts of things. So the key thing is not so much the magnet shape, although that does have an impact on the performance in terms of mechanical variation. Smaller diameter magnets typically have more sensitivity to off-axis errors in the mechanical setup. But really any magnet shape can be used as long as it fulfills the requirements for the magnetic field range of the sensor. So as long as you're above 5 milliteslas and below 50 or below 120 milliteslas or below 130 milliteslas for the z-axis, the sensor will operate correctly and you can usually compute an angle from that.
Great, thank you. I'm trying to keep up with all the questions. This one is on data integrity. So how do you ensure data integrity during transmission?
Yeah, that was
that already. No.
We covered that for the earlier slide. So that's the question about the CRC, or the CRC slide, where we included a CRC to cover the data measured to ensure that the data measured and the readback is not corrupted during transmission.
Great, thank you. And I got a couple more, but I think we're running pretty much out of time. I'm just reviewing the questions quickly to see how many we can answer. For XYZ detection application, what magnet shape, as in magnet field orientation, would you recommend? Would you recommend to have another magnet on the sensor to eliminate stray field?
Theoretically, could be possible, but I don't believe so. To detect X, Y, Z magnetic fields, that's usually going to be more common like a joystick application. If I flip back here, and then the example magnet you see here is an axially magnetized rod magnet. And as that magnet moves around in free space, as long as it's pointing towards the sensor in a gimbal design, you'll always be able to sense the magnet traveling along that surface of the sphere. So for me, this sort of magnet configuration is best suited for that. However, that does not mean other magnet shapes, orientations cannot be used. You could use a diametrically magnetized magnet, for example, just requires different processing inside the host microcontroller. In terms of shielding, I don't believe that another magnet is probably the best way to go there, but rather some high permeability material like nickel iron, mu metal, those sorts of materials can be used in order to help shield from stray magnetic fields.
Thank you. Would you be able to go back to the first slide, please, for this question? This will be the last question. So you had mentioned a power consumption of something like 6 NA in the first slide. What type of application is this based on?
It's not really based on the application. That's simply how the sensor operates. So in the idle state, when it's not acquiring data, when it's not acquiring a magnetic field, it is in this kind of sleep mode where it's drawing 4 milliamps of peak current, or sorry, 20 milliamp, 20 microamps of peak current that you see here. On average, so when you do an average calculation, you average down to, let's say, 10 microamps, 100 microamps, depending on the duty cycle of the sensor. In that case, it can be for a variety of different applications, like situations where you need to put the system into a low power state and then wake it up. And one example for this is things like battery powered joysticks for robotic applications, where you have a kind of box that's battery powered. You have a joystick to control a little robot. It's wireless. If you want the thing to shut down but wake up when you move the joystick, the 90395 and the wake and change functionality can really help with that. And that's when you put the IC to sleep. It goes into this low power average mode where it detects that the joystick gets nudged, and then it wakes everything else back up, and then it can go back into the wireless transmission state, angle computation, those sorts of things.
Great. I think that's all the questions we have time for. There's a couple unanswered ones, the more specific ones to people's personal applications, but we'll get back to you after the webinar. Would you like to share the results from the poll, Nick?
Sure. They should be on the screen here. So in terms of whether or not 5 volts or 3.3 volt supply is good or bad, you see it on the screen. Looks like the majority is in a mixed configuration. So 60% say that 3.3 volt is okay, or they can use either. Apparently 11% say that only 5 volt is available today in their system. And then, yeah, 29% say that they can't comment, presumably because they're not doing design-in activities for the 90395 or 90393.
Great, thanks, Nick. And there was one last question relating to the slides. Yes, we will share the slides and the recording of the webinar. This has been recorded, so it's all available afterwards. Don't worry. I think that's all for today. Thank you very much all for joining us, and thank you, Nick, for the great presentation and for asking all the questions.
Thank you as well, and thank you everybody for your time. I hope we answered all your questions. If not, feel free to contact us.